Okay, good morning. Let's see. So, in the class on Monday, we were discussing about the Dirac equation and specifically the origin of spin of electrons. And so the plan today is we'll kind of wrap up that discussion, and we'll see that the Dirac equation not just shows the reason for why there is spin, but it does a whole lot more of the other things. So we'll just briefly discuss about that. It predicts the existence of antiparticles and things like that, which have been observed, and essentially it gave birth to the whole field of quantum field theory and all this zoo of particles, new particles, bosons, fermions, all these things that people measure in colliders and such things. And its manifestation in condensed matter systems is the very interesting aspect. So what we are going to I'll spend maybe the first 15-20 minutes finishing up that discussion, and then we'll start discussing about one of the experiments which kind of very nicely combines not just the Dirac equation, but also a relatively very new finding in general in quantum mechanics and such is this Berry phase, right, which is one of the precursors of all things topological and such things. So we'll discuss about that today. Okay, so I'll start from where we left in the last class, and what we had managed to do was from special relativity, we realized that the energy of a particle is not just p squared by 2m, but it looks like mc squared plus pc squared, right? So that's what the total energy of a particle looks like according to special relativity. And I'll just bring up the slides so that it's in the background here. Yeah, so I think what you can show here is if the particle is moving slowly compared to the speed of light, then this term is very small. The momentum is mass times its actual velocity, and so this term is very small. So you can take out, this is very big, so you can do a Taylor expansion, and when you do that, what you'll see is this is just p squared by 2m. That's what you're looking at with a Taylor expansion, right? And that's what we conventionally thought was the kinetic energy, but then there's this part which is the rest energy of the particle, right? But for dealing with it, making the equation, taking it from a classical mechanics to quantum mechanics, we essentially the efforts were to first look at it and say that, well, I can rearrange this and write it as e squared minus. Well, I think we kind of went through that. I don't want to essentially rederive it all over again. But you can write it in a form very similar to Maxwell's equation, and use that energy is time derivative operator, momentum is spatial derivative operator, right? And you mix it, and if you try to do this in the energy square, so this is energy square, right? Del squared and d by dt squared. So that's what we call as the Klein-Gordon equation, which looks something like a Schrodinger equation, but it's actually in the square of time. Schrodinger equation is IH bar d by dt is one derivative in time. And what it was found was that this equation, the Klein-Gordon equation, fails to satisfy a positive definite probability density. It can actually become negative. And there are various other discussions. I'm not really getting into other things, but essentially it cannot represent particles that have spin, and I'm not giving you this discussion why. You can kind of read that up, I think. So it cannot represent electrons, and for that, what Dirac did was essentially he took a square root of this whole thing on the left side, and what he finds is the equation, essentially what he did was del squared minus 1 over c squared. He was able to write it as the perfect square of plus I and d over c del by del t. Okay, so basically he was able to find these coefficients a, b, c, and d, so that once you have this, you realize that the equation will be, instead of taking the energy square as the operator, you can just take one of these factor 2's here, and your equation, the quantum mechanical equation, then will become d over c. This c is speed of light, not this coefficient. Psi is equal to the Compton mc by h bar, right? Yeah. So the Compton wavelengths. So that's your Dirac equation. And these are what he found was, in order to do that, I think what we had briefly discussed in the last class was that a squared, b squared, c squared, and d squared have to be equal to 1, right? According to, by just matching the coefficients. A squared is del x squared's coefficient, so 1 here and so on, and no cross terms. No cross terms would mean AB plus BA would be equal to 0, and you realize this is an anti-commutator, A comma B. You can think of it that way, anti-commutator. Commutator would be with a minus sign. Okay, so this is typically not how the equation is written. The equation is written slightly differently. It's written in terms of what are now famously known as these Dirac matrices. So, first things first, we discussed that these ABCDs cannot be numbers. They have to be matrices. And he actually was able to reason out with the help of mathematicians and such, is that these are 4 by 4 matrices minimum. Not 2 by 2, but 4 by 4 matrices. And a slightly different way of writing the same equation really, but in a slightly different way, is in terms of what are called these Dirac matrices. Let me just write it down. And okay, gamma. So we're going to use now a 4-vector notation. Remember, in 4 vectors, we have always used 0, 1, 2, and 3, where 0 is the first component, 1, 2, and 3 are the next 3 components, right? That's what we have used for relativity. So for example, your 4-vector distance was ct, comma, x, y, z, right? And similarly, the 4 momentum was energy over c, comma, px, py, pz, right? In a similar way, we are going to write these. We're going to actually define these quantities. I mean, this is just a definition at this point. Nothing very fancy. Gamma 0 is the first Dirac matrix. It's a 4 by 4 matrix, and it is actually just equal to this D. And when you look at D, I'm not kind of trying to write them all out, but D and D inverse are the same. So you can write it as D or D inverse. And similarly, gamma 1 is related to, I think, IA and all that. I don't want to kind of write it. So they're just related to, I think probably there's a D inverse A or something like that. So these are 4 Dirac matrices that come up. That's also gamma 1 and gamma 2 and gamma 3. So there are 4 Dirac matrices that will come out of here. And if you kind of look at it, how do these matrices look? What's very interesting is the gamma naught, for example, is a 4 by 4. What it looks like is 1, 0, 0, 1. So that's the identity matrix. Then you get all zeros, and then minus 1, 0, 0, minus 1. So this is how, for example, as you know, matrices, they can have many representations. You can actually linearly kind of mix them up and all that, but this is one representation. Similarly, if you look at what is gamma 1, what you'll find is this is actually 0. This is the Pauli spin matrix now, sigma x. Pauli spin matrix, sigma x and minus sigma x and 0. And similarly, sigma 2 would be Pauli spin matrix y. and sigma 3 will be Pauli spin matrix Z. Okay, so for example, the Pauli spin matrix 1 would be 0, this one is 0, 1, 1, 0, something like that, for example. Right? So these are spin matrices. Okay, so what's interesting about these matrices is actually gamma naught square will be equal to identity matrix or 1. I mean, that's what it is. Gamma naught square is identity matrix 4 by 4. You can take it and you'll see all diagonals will be 1. But once we make this transformation from A, B, C, and D, so there's actually, when we define this gamma 1, there's an I sitting in front of you. So as a result, what happens is this gamma matrices, gamma 1 square, gamma 2 squared, gamma 3 squared will become equal to -1 because there's an I. So it looks. And indeed, so what you'll find is, again, this is really not terribly useful for this course, but a very interesting relation between these gamma matrices is you can take the gammas and find their anti-commutator, which is, let's say, I don't want to use, well, okay, let's just write it once. So typically it's written as nus and mus. These are the coefficients. Nu and mu, two coefficients. Each of them can run from 0, 1 to 3. So that will be, well, gamma mu plus gamma mu, right? So, and I think you realize it's matrices, so they don't necessarily commute. And when you do that, you kind of realize right away is that if nu and mu are equal, then you will get either a 1 or a -1. Right? You'll get a 1 or a -1. And if you look at which ones will be 1, only gamma 0 squared will be 1, all the others will be -1. And if you go back and look at, there's actually a very interesting connection, which I will not get into in any depth, but it's very interesting connection between this Minkowski tensor. So basically gamma square is equal to the first element, and gamma 0 squared is first element, and gamma 2, 1, 2, and 3 squared are the next 3 elements. So this kind of, so this result actually you can write it as 2 times G nu mu. G is that tensor, Minkowski tensor. That remember we basically Minkowski said that this is the invariant quantity, right? Because if you take x and you measure it in one reference frame and you go to another reference frame, what is always conserved is ct squared minus x squared minus y squared minus z squared, not plus. Okay? So the sign convention is plus minus minus minus. Okay? Plus minus minus minus. Okay? Okay, so if you put as you can see, if you put gamma naught, you get 2 gamma naught squared. What is gamma naught squared? It's plus 1. Right? So you get 2 times 1, 2. Right? And if you get gamma 2 squared, gamma 1 squared, and all that, you get -2 here. That's all it means. And there's a very, actually kind of very interesting connection between this and what's mathematically known as Clifford algebras and Grassmann algebras, which we don't need to bother about at this stage. But if people are interested, you can follow up on that. It's definitely led to very interesting concepts in physics and such things. Okay, so if once we define it this way, the Dirac equation is written in a very elegant way, or a very economic way in some sense. So you can kind of, instead of writing this A, B, C's, and D's, what you write is you can just take this equation and replace my gamma matrices and write it as gamma mu del mu minus. That's your Dirac equation. And what does this notation mean? It means whenever I have mu and mu here, that means I'm summing over all possible indices, 0, 1, 2, and 3. That's what it means. And then that's basically this sum here. So the 0 term, if you know now, del 0 would be 1 over c del by del t, right? You realize because my indices are 0 is time, c times t, right? So that's how it's going to be. Similarly, del 1 would be del over del x, and so on. So this is really the full-blown Dirac equation. but it's written in a nice and compact way. Sometimes this term here, I forget, I mean probably this term, or this is written as del slash. It's Feynman introduced a slash notation just to make it even more economical maybe, or something like that. But anyway, that doesn't, these are all notational things which we don't need to bother. Okay, so so that's your basically end result. And you see now, very interestingly, these are first derivatives in time and first derivatives in space. D by dt and d by dx. Very different from Schrodinger equation or Klein-Gordon equation, where you have at least one double derivative, right? Schrodinger equation has two derivatives in space, or the Laplacian, and Klein-Gordon has two derivatives in both. So whereas here, this is the first derivative in all. And once you look at this one, then you can conserve, probability density can be positive definite and all that. It solves that problem. Okay, so now what is the fallout of Dirac equation is the more interesting, rather remarkable thing. And generally, you would go through, as you can realize, this is written in a very compact way, but it's actually many equations, coupled together and that sort of thing. Let me just discuss just briefly what is the free particle solution to this problem, to this equation, the free particle. A free particle from Schrodinger equation was e to the power ik dot r, right? E to the power ik dot r by square root of some normalization volume. That's your Schrodinger equation solution for a free particle, right? Now the question is, what is it for the Dirac equation? And immediately you realize here that psi, because all of these are 4 by 4 matrices, right? Psi has to be a 4 by 1 vector. It's a 4 by 1 vector. It's not a number anymore. It's not a scalar quantity, which we have in Schrodinger equation. And I'm not going to get into details, but let me just write down, because what you need to do is kind of solve a few things. These are all equations, del by del t, and you try some solutions which would look like, maybe u of r, I k dot r, and then things like that. You'll try some things like that, right? What you will end up with after you solve these, 4 coupled equations is for a free particle, it will look like this. So psi, for example, one of the psi's is going to look like 1, 0, free particle, okay, so 1, 0, and there will be like a Cp over energy plus something. I mean, again, it's not, the reason I'm not writing out all the details is not terribly important right now. Px plus Ipy over some energy plus some other thing. So there will be basically 4 vectors in the, 4 numbers sitting in those 4 points, right? And then you'll get a e to the power minus I mc squared over h bar t. Time dependent solution. See, now in Dirac equation, you can't get away from the fact that, this is a complete, time and space are treated equally, right? There's no such thing as time independent or things like that. This is a fully, space and time dependent thing. And so for small momenta, so this will be one, so you'll have 4 of these. And then this is kind of the interesting part of it. You'll have 4 of these. So let's write it psi 1, psi 2 will be 0, 1, and then be something else here. 0, 1, and then something else here. And it will be, and okay, so that's what will happen. And let me just actually make the assumption now, if your momentum is much smaller, just like we discussed earlier, if this term is much smaller than the rest energy, then these 2 terms are very small. So you can assume it to be 0. And it's an approximation. Take it to be 0. So I'm just going to make that approximation. So let's say the momentum is very small. So we are going almost, not almost, we're going, the speeds are non-relativistic. So v is much less than c. Then these terms basically kind of go away. And you get zeros. And you'll get 3 and 4. And for them, it will look like 0, 0, 1, 0. But strangely, the sign will flip from minus to plus. And psi 4. Again, this is one representation. As you know, wave functions are not unique, but it's one representation. So that's what for free particle sort of solution. And let me just mention at this point that these two are particles that have energy. If you kind of look at this wave function and apply the Dirac equation, the energy will be mc squared plus pc whole squared, right, with square root. But for these two, it will be negative. So negative energy. Minus sign. Right. And what was I going to say? Yeah, so these are, so for example, this would represent electrons, but clearly now what you can already see that, this electron state is different from that electron state. And this is what you would call as a spin up state, for example, let's say. And that's what you would call as a spin down state. This is where the spin comes. Right away for a free particle, you directly get spin. So that's all good. The interesting thing is, what is this? And this is essentially many ways to look at it. This was a major point of contention when Dirac initially introduced his equation. But he basically said that the equations are so compact and mathematically elegant, it must be true. So that was his very interesting belief. And so it was predicting some particles with negative energies, or what you can think of it is this is going backwards in time. One can look at it that way. Don't want to get into too much details, but this is what these are positrons. This is electrons. This is the antimatter and antimatter, positrons. Different from holes. There is some little bit of analogy, but it's different from holes. Positrons are not holes, but kind of like that. So at that time, he was obviously kind of somewhat ridiculed also for predicting this. But it took only probably like 4 years for people to discover experimentally the existence of positrons. From cloud chambers and cosmic rays, you can basically, the idea is if an electron with one of these things here comes along and a positron comes along, they can annihilate each other and emit just light. So this will be bringing in maybe mc squared. This will bring in anyway. So basically the total energy of let me not get into all the details here. Okay, so that's, and positrons are, I think we know that even in campus here we have the chess has 2 rings. There's electron ring and then the positron ring. Positrons are used in PETs, positron tomography, for medical purposes today. And they're interestingly also used for measuring what are called point defect densities in crystals and semiconductors. Point defects. Remember, you have solved problems on scattering from point defects, missing atoms. So if you want to measure what's the density of missing atoms, it turns out it's extremely difficult. But if you shoot positrons at it, it kind of measures the missing mass. So because it's antimatter, it recombines with matter. So whatever is left over, you can back up from there. What is the vacancy density? So it's used for things like that, positron annihilation measurements for semiconductors. It's heavily used for semiconductors, actually. Yeah. Okay, so let's see. So at least hopefully it's clear that the spin emerges naturally from here. There is no need to ad hoc introduce it in an ad hoc manner. But if you kind of now forget about one component of it, if you're heavily non-relativistic, very slow, then these terms are kind of 0. So you reduce to the Pauli version of it, and you get the Pauli spin matrices. And essentially, your total Hamiltonian now becomes a Hamiltonian with no spin, plus you will have a Bohr magneton, plus if you have a crystal. Again, I'm not derived this, but these are relatively kind of standard E cross V over C squared. Some terms basically that look like that. So there's a spin orbit coupling and then a direct Zeeman splitting of electrons because of spin. And what Dirac equation was able to do was, so Pauli's spin matrices were able to explain some splittings, but there are some extra very fine splittings that they couldn't explain, and Dirac completely explained every little, peak and every little splitting with magnetic field. But as you know, in science there's never an end. There's some other additional shift that was found. It's called the Lamb shift and all that, and that led to Feynman and Schwinger and Tomonaga with the quantum electrodynamics, which is a little further from here. Anyway, so we are going to kind of now look at, or rather kind of stop this discussion of Dirac equation, but hopefully you saw the procedure by which he ends up here. So, any questions on this? Okay, so if not, so what we'll do then is, it might seem like I'm taking a departure now from Dirac equation, but it's connected. I'll come back. But the next topic I want to cover is this the Berry phase. Okay? So that's what we're going to discuss, and I'll make the connection back to the Berry phase with the Dirac equation. Okay? So the Berry phase, I think yesterday also, I think Kevin and others presented. Is motivated, we are going to motivate ourselves from this experiment from transport, which is the quantum Hall effect. There are many others. There's anomalous Hall effect, there is polarization, there's magnetization, all kinds of things which can help you, essentially which needs Berry phase to be able to explain. But we are going to start with this. Okay, so the quantum Hall effect. I hope you have seen this by now. Essentially, a normal Hall effect is you take a piece of semiconductor. Let's make it simple. Take a two-dimensional electron gas in a silicon MOSFET or in a gallium arsenide or some heterostructure two-dimensional electron gas, and you make contacts like these, ohmic contacts, 6 of them, and then you apply a magnetic field that goes perpendicular to the plane of the electron motion. And then you measure the Hall resistance, which is basically the resistance is voltage over current, but here Hall resistance is the transverse voltage here divided by current there. So Vxy divided by Ixx. So the transverse. And I think Edwin Hall, obviously in 1870s, 1880s, already had found that a simple classical reason why there will be a voltage, because you have magnetic field, you have a Lorentz force, electrons get slammed into one contact and the other charge neutrality is positive on the other side, so there's a voltage difference because charge piles up. And so what happened in 1980 was, so Klaus von Klitzing in high magnetic field lab in France, so he was measuring the transport in a silicon MOSFET with a 2D electron gas. This is not graphene. This is not any fancy, 2D electron gas and topological insulator. This is the most useful electronic device we know today, right? Silicon MOSFET. So he took that, created the electron gas, and he was measuring the Rxx, Rxy. So there's a gate, and he creates the electron gas, and he ramps up the magnetic field to very high values. This is not von Klitzing's experiment. I think there he went up to a few, 14, 15, I forget. Basically it was a high magnetic field. And so classically, your resistance is 1 over n times electron charge. So it goes linearly. The classical Hall resistance goes linearly with magnetic field. B times 1 over ne or something like that. And here, what you observes is these very precise steps, and the steps in the resistance are exactly at h over e squared. I think you realize right away this is the quantized conductance. Landau 1 over that is e squared by h is the Landau conductance, right? So that's, that was obviously somewhat weird, and at that time, so the understanding was because of a magnetic field. I'm going to just qualitatively talk about it first, and then we will discuss it later in some detail. So in the absence of a magnetic field, the electron gas has an energy that looks like this. And its dispersion looks, parabolic, let's say, right? Something like that. I mean, maybe you can take into cosine functions and all that. But if you apply a very large magnetic field, classically, so these are propagating states. The electrons can go, like that. But now if I apply a very large magnetic field, classically the magnetic field is essentially going to make electrons go in circles now, right? So it's going to do cyclotron orbits like that, right? And if you ramp up the magnetic field, the radius of this shrinks, right? It gets smaller, right? So higher is the magnetic field. And what you can show is in the end, if you solve this with our prescription from Dirac that, Hamiltonian is Hamiltonian without spin plus, mu b sigma dot b. Forget about spin orbit coupling for a second. You just take this spin term and resolve your Hamiltonian. Your eigenvalues will look omega c n plus half. Eigenvalues get quantized. So what is omega c? This is h bar omega c is the cyclotron, omega c is the cyclotron frequency, electric charge, magnetic field by effective mass of electrons. Very simple result. I think, you could, well, in hindsight, you could say that, well, it's like a harmonic oscillator now. So harmonic oscillator equations. N is an integer, and it's kind of the number of Landau levels. And, so essentially what has happened is you took an energy dispersion that looked continuous. Let's plot it this way. So the density of states for this was looking like, it's a 2D electron gas, so it was a constant. I think we have talked about that. Right? 2D electron gas, if that's your dispersion, then the density of states is m star over pi h bar squared starting from 0, wherever is the minimum of the band. But now what happens when you apply a large magnetic field is essentially a bunch of these energies of, of width h bar omega c, they all collapse into one level. That's what happens. For n is equal to 0, you'll have a level. So what I'm trying to say is, this bunch of density of states will collapse into, you turn up your magnetic field, this bunch will collapse into 1. Basically there will be a number of states here. How many states? Well, m star by pi h bar squared times h bar omega c, right? That many states are going to collapse into one state. That's called a Landau level. That's the energy of that state. N is equal to 0, n is equal to 1, 2, 3, and so on. So this whole density of states collapses into a string of this Dirac delta sort of picture. That's what happens. This is plain quantum mechanics. This was known before quantum Hall effect. There's nothing fancy about that. And now, with a gate voltage or with a magnetic field, what you're doing is that clear? What I just said. So essentially, you're changing the density of states with the magnetic field, and these are called Landau levels. Okay. And you have a certain number of electrons filled. Because of disorder and defects and things like that, I know. I think you know that in physics there's no exact Dirac delta. Maybe there's some broadening. Maybe. Typically, the broadening is of the order of h bar over gamma, where gamma is one of the scattering times, mobility related and things like that. Right? H bar over time as units of energy. Right? So that's order of magnitude of broadening. So you need a very high mobility in order to see things like this. If your mobility is terribly low, these things are kind of, do that, and you won't see anything interesting. The mobility is too low. It's very broadened out. Okay. So what you're doing with magnetic field is you have a fixed number of electrons. Your gate voltage has said, well, I want 5 times 10 to the 11 per centimeter square electrons in the 2D electron gas. So I started out with, maybe I was filled up till here before I applied a magnetic field. And I apply a magnetic field, collapse all these things here. And maybe what has happened is this thing is completely filled and this is partially filled, maybe. Okay. Right? So if it's completely filled, that thing is not going to contribute to any current. It will not contribute to conductivity. Completely filled band, no conductivity. and partially filled will, right? Something like that. Classical, I mean, I'm just thinking about that in that perspective. And therefore, so the conductivity will be proportional to how many electrons are there at this density of states, and all that. And as you change the magnetic field, the total number of electrons is not changing. What is changing is these things are getting spaced out or doing that. So as you see, kind of going through, electrons are here, and then you're giving it a large density of states, a small density of states, large, small, as your field goes up, increases or decreases. Right? You are sweeping. Basically, you are the comb is being stretched out. So the number of electrons at the Fermi level, or at the Fermi level, the density of states at the Fermi level is oscillating with magnetic field. And as a result, from there itself, I think you can realize conductivity is proportional to the density of states at the Fermi level. That much you will agree. Right? Electrical conductivity, you measure resistance and things like that, is proportional to how many electrons are there at the Fermi level, and the maximum electrons you can put is the density of states. So as a result, what you expect qualitatively is that as I change my magnetic field, my conductivity should oscillate. I mean, that's something you expect. And this is called a Shubnikov-de-Haas oscillation. And this was observed way before the quantum Hall effect. Shubnikov-de-Haas oscillations. So it's oscillations in conductivity, or you can plot resistivity. It will do the same thing. Basically start oscillating. And it's used heavily, for example, to measure effective masses, scattering times, and things like that. This is Shubnikov-de-Haas. This is a whole lot different from Shubnikov-de-Haas. This is the quantum Hall effect. What is very surprising in the quantum Hall effect, the most surprising thing is, you get these conductance quantizations, right? Like 1 times h by e squared, and so this is the integer quantum Hall effect. But what is the most surprising is how precise is this step? How precise is this step? So, for example, if you do the measurement by, this is now, so I think the latest numbers, this resistance value that you measure is 1 part in billion or better. Now, the precision is 1 in 10 to the power 9. And that is very weird. Nothing in Shubnikov-de-Haas, these will tell you why it should be like that. So that is very strange, that the precision at which this integer quantum Hall effect resistance appears. Now, this is the standard of resistance today. National Institute of Standards and Technology, NIST, they use this as the new resistance standard. Right? And it's, well, fundamental constant, so I think makes sense. So what was very weird is, why is it that it's so precise? I mean, nothing in transport that we have done tells you that I should get an integer and with such a great precision. And that's where all this stuff with Berry phase and topology will come in. So we will actually discuss that, and we'll come back to this and discuss again some more details of this. But I think the main motivation is, why is it so precise? If you just do your standard Shubnikov-de-Haas or transport theory with a magnetic field, you're not going to be able to explain why is it, 1 part in 10 to the billion. It's not possible to explain it. And so actually, very interestingly, just 2 years after this, there are a group of 4 people. So I think it's called the TKNN. David Thowles at Washington and Nightingale. I mean, few people made a very interesting connection to the conductivity, and what they found was the following: that they could write that the conductivity will be E squared by h times, and then this is what we're going to discuss today for the rest of the class, something d2k. So we are 2D system, so it's d2k times. Basically, we're going to actually discuss this today. Okay, so what they find is you do an integration of something in the k space, and what they find is this number that you get when you integrate this over a closed surface. You are guaranteed that this will be an integer. It's guaranteed to be an integer. That's what they find. They were able to write the conductivity, the Hall conductivity, in this way. And this guarantee is actually guarantee as in mathematically guaranteed. It's because what we'll find is what it is counting is kind of a number of holes on a three-dimensional object. There can't be 1.5 holes or 1.2 holes. It's an integer. I mean, that's kind of almost a definition of an integer. And an integer, I think we all know, integers are special numbers, right? And then there's nothing ambiguous about them, right? So very precise. And what they are able to relate that the conductivity, electrical conductivity, is related to this thing, and this is what's called the Chern number. What we'll see is actually it's very interesting, very simply also connected to Gauss law, where you count, if you take a volume, how many point charges are inside that volume. It's actually pretty much similar, not much different. So we're going to see that, and that was that was found to be actually exactly related to the Berry phase. What is actually remarkable is they wrote the paper in 1982, 2 years after the quantum Hall experiment came out in 1980. But Berry and the Berry phase came in 1984. So essentially, they obviously they didn't refer to Berry phase, but they make the connection that there's something interesting going on. And then Michael Berry figures out that there was something missing. After half a century of quantum mechanics, somehow people missed a very interesting thing, which is the Berry phase. So that's what we're going to discuss now. What's the connection between these things? And this thing is basically an integer, and this phenomena explains the integer quantum Hall effect. And what is interesting is what we'll find now is you can actually take whatever surface this will be integrated over. You can deform it, due to some defects and all that, but the Chern number will not change. It's a it's an invariant, meaning it doesn't depend if you kind of change the surface from a sphere to an oval or something like that. It doesn't change. So that's very interesting. Okay, so let's actually go back and look at some of the ideas behind this. And in fact, this thing is so that's we're going to again step away from quantum Hall effect and discuss some very kind of nice mathematical results, which I think you all have seen or thought about probably once in a while. But the way this is brought together, and connected to the transport problem is very exciting. At least for me, I find it very interesting. So we'll start with this problem, and now we are basically talking about some very simple geometrical ideas, and because the Chern number these are geometrically, come from geometry, so I think you may have seen this picture. So if I take a tetrahedron like that, right? A tetrahedron like that has a certain number of vertices, right? Certain number of vertices, certain number of faces, and certain number of edges, right? You may have seen this. There's a relation between them. If it's a convex polygon like that, then it turns out that vertices minus edges plus faces is equal to a number, and it's an integer. Of course, you have an integral number here. So what is very amazing is you can actually we'll discuss that now. This is obviously a discrete object, so there are integer number of things. You can now completely deform it, make it curved surfaces. There's no clear edge now, and you will still get this. So this is, what do we mean by vertices, edges, and faces then, right? That's kind of a question. So this was known by Euler way ago. One of the masters of mathematics, right? And this is called the Euler characteristic. And what he kind of missed, even Euler, a great mathematician, I think what he missed, and I've read about in a couple of opposing stories, but I think it's correct that he missed it. So I think you can test it. Many you can take shapes and all that. But that what he missed was if you actually take this and you actually put a hole in it. If you had an object also like that, but you actually maybe I don't want to draw that, but anyway, so you have a object that actually has a hole in it, but it also has number of faces and edges and so on, then this is not correct. So what you will get then is there will be minus 2 times a number of holes, and even Euler missed that. So the new Euler characteristic in some sense now is so you can take a much more complicated object now, right, which has holes and things like that, and you'll get that minus 2 times number of holes. Okay, so now kind of and the next part of it is kind of goes back to Gauss, and that's where many of these big changes happen. So Gauss basically starts thinking about this problem and says that let me try to look at what would be a generalization of this. Actually, I think the way I'm thinking is just thinking, well, no, actually, here's the real story behind this. So Gauss was commissioned by the forget the king or something so he was commissioned to draw a map of a certain area of Prussia in Germany. And so he, obviously was a very astute mathematician. But what he was trying to understand is, in a map, you want to understand whether something is curved down, curved up, and things like that, right? So in a way, before him, people always thought that in order to measure the curvature of something, you have to step out of that surface and look at it from outside. I mean, then it's clear. You have a little dent or you have a bump or whatever. That's clear. But what Gauss found, and this is, Gauss has obviously many, many theorems, but according to him, this is the most remarkable theorem of his whole career. And it's the simplest way to state it, is that to find the curvature of any surface, you don't have to step out of the surface. You can do measurements on the surface itself, standing on the surface, and you can figure out what is the curvature. You don't have to step out of it. And this is called this is a remarkable theorem. I mean, this is so you can imagine this very strange theorem. It's saying that I can tell you what is the curvature, whether the surface I'm standing on is curved or flat, without stepping out of it. And I think you might have seen or heard about these, probably some puzzles that, well, one of the nice puzzles is, so a bear, right, starts walking 1,000 miles to the south, then takes a 90-degree left, walks 500 miles west, and then takes a 90-degree left again, and walks 1,000 miles north, and is back where it started. So what's the color of the bear? So you have heard about that probably, right? So then that means it has to be on the equator, right? So okay, so now you see very interestingly, your triangles don't quite add up to 180 degrees. Right? You take 290 degrees, but you end up with something here, right? And so what he says is, I'm going to basically, on the surface, I'm going to do measurements, measure angles, measure lengths, and all that. And for example, if my angles don't add up to 180, I know it's curved. Right away, I know it's curved. Right? And things like that. So that's called a defect in mathematical parlance now. And so what he does is he actually, and as you can imagine, that really cut down his work by a great deal, right? Because he had people basically just measure things, and he didn't have to step on a mountain or high level to find out the curvatures. He used this, heavily for his experimental work, for his work. But what he does next is he kind of realizes that it is the mathematical theorem that kind of almost proves that, in some sense. So that's one idea, that you don't have to step out to find what is the curvature of an object. But curvature itself, he gave a very accurate mathematical meaning to it, and the mathematical expression for curvature that Gauss derived is something you use all the time now. It's the double derivative, right? The double derivative of a function. So you can imagine the surface here, is a function of, say, x and y, right? It's a function of x and y. Let's call it maybe f of x and y, right? And what is the curvature here? Well, if you are in a 2D surface in a 3D space, you don't have only one curvature, you have two, right? As you can see, you have two linearly independent curvatures. You have one, for example, maybe along the x direction and one along the y direction, right? Curvature along x, curvature along y. Right? And so you can take del x squared and del 2 del f del y squared, right? These are the two curvatures along the two directions. And what Gauss was able to do was generalize this Euler theorem to what's now called the Gauss-Bonnet theorem. In fact, he didn't quite publish it. Bonnet did later, but because Gauss thought that his anyway, so he had already derived this earlier. But typically this written, there are some cross terms, and you can kind of write it back in this term. I'm not getting into all the details here. But so that's curvature 1, that's curvature 2. And you know this is a point function, meaning it's defined at all points. It changes as you go from one point to another. And if you take the product of the two, kappa 1 and kappa 2, and you integrate it over a whole closed surface, let's say dx dy. You integrate the product of the two over a whole closed surface. Then what you're going to get is 2 pi times 2 minus g, where g is the number of holes in the surface. Holes sometimes it's called the number of handles on a sphere. It's the same thing, really, kind of number of holes. And then that's the definition, or that's the Gauss-Bonnet theorem. And we'll see it plays an interesting role in the Berry phase picture as well. So just as a sanity check, if you are on the surface of a sphere, what is the curvature of a sphere, perfect sphere? Curvature is 1 over r, right? 1 over r, 1 over the radius is the curve. You can, anyway, you can kind of work that out. And what you will get then is when I integrate it, I'll get 4 pi r squared dr, 1 over r squared, right? And I think I will end up getting 4 pi when I integrate it. I think I missed a radius square, right? So yeah, k times r squared or something. Yeah, it should be obviously dimensionless. So r squared, no, this is fine. So just check this out. I think you'll get a 4 pi. I mean, this is basically your 4 pi from the Gauss law of electrostatics, where you get 4 pi epsilon. This is the same thing, really. Over, for a unit radius, this is the surface area of that surface. Now, what is very remarkable about this theorem is not just, oh, you're getting this formula, but what it's saying now is you can take the sphere and you can deform it as much as you want. You can make it a, very narrow and a long cigar, or something like that. As long as you don't puncture it, don't push a hole through it, no matter what surface you go to, you will always get the same number on the right side. It won't change. And then that's kind of the interesting thing. So as you can see, some curvatures will increase, some will decrease, but on the whole, when you integrate it, you will always get this. So that's the statement of the Gauss-Bonnet theorem. So from there, I think you can tell me maybe if I take a donut, what would be my total Gaussian curvature? What's the Gaussian curvature, meaning what's the right hand side if I have a donut? Right? A donut has one hole, so g is 1, so this is 0. Okay. So that has a Gaussian curvature of 0, and again, if you have 2 holes, and so on. Right? In some sense, this quantum Hall effect is what's going on in K space. You're burning a lot of holes in your surface of Brillouin zone surface, and these numbers that appear are these numbers here. But in some sense, not exactly right, but connected to that. And as you can see, there is no real ambiguity about how many holes there are. It's very precise. It's an integer, right? So that's why it's. Okay. So another example of that would be, what if I had a This is a trickier one, but I think it illustrates a very nice point. What if I had a cylindrical surface, a cylinder? Let's say I take a paper, turn it around, wrap it like that. What do you think would be the curvature of this total surface here? A cylinder has how much curvature? So I think you may be trying to apply this, but I think you can actually look at a cylinder and you realize that if I calculate my two curvatures, right, you right away see that the curvature in one direction is 0. There is no curvature in that direction, right? So the total curvature of this is actually 0. And this is another thing that actually is captured by the Gauss's remarkable theorem that if you in order to have curvature, rather if you start with a flat surface and you don't stretch anything, you can bend, you can do, but don't stretch, don't apply strain to it. Then if you take a flat surface and you create anything out of it, you will always get a total curvature of 0. If you started with a flat surface and you don't stretch things and all that. And conversely, if you start with a curved surface like a sphere, no matter how hard you try, you cannot make it flat. I think we know that, at least intuitively, right? And the product of the two also is responsible for, I think you may have seen it, is the reason why you can hold a pizza when it's elongated this way. So if you bend it this way, it becomes rigid that way. The curvature becomes fixed, because you curve it one way and the other curvature. So that's how it helps to eat pizza, I guess. Yeah. So those are all these very interesting aspects of the Gauss-Bonnet theorem. Okay, so now there are this has been generalized to a great degree in mathematics now, into the called these index theorems and all that. But I don't think it's necessary for what we need to talk about in the class today. Yeah. So what we'll do now is go from here and start looking at Berry phase. I mean, so we'll connect this to the Berry phase now. Okay, so what is Berry phase and how does it come about? Let's make the connection now. So Berry phase is actually experimentally was observed a long time ago. I mean, I think 40s or 30s, and many of these weird objects like the Harnow-Bohm experiment, you can explain it from Berry phase as well. But here's a beautiful experiment which I think really explains, tells you that there's something weird going on here. So you can think of an experiment where you take just a optical waveguide or a optical fiber, and you shine into it a laser, okay, and the mode of the laser is such that there's only one mode that goes through this. So light comes in here, gets out here, things are all fine. When light goes that way, its momentum or the pointing vector is pointing in that direction. Light going that way, and we are free to at least choose at this point some polarization. Let's choose that the electric field is going, maybe in that direction, and so if the pointing vector is that way, the magnetic field is coming out of the plane like that, and so it goes through and it comes out like that too. Right? Polarization is like that. Now, what you can do, and this is what people had done interestingly experimentally first, and then they were trying to figure out what's going on. So what you can do is take this fiber and you can physically bend it. You bend it maybe in some contorted way. Maybe, I don't know, I'm just going to come back. Oh, sorry, I think this is the wrong way here. And such that it comes back and light essentially comes back and when it comes out, it's back into the same direction again. Right? Same direction again. Right? So the question is, what's the polarization of this? And the very interesting fact is the polarization really depends on how you bend it. It remembers that. It need not be exactly on the board, but it can turn at a certain angle alpha. will turn. And that alpha, this is a classical Berry phase in some sense. It's called the Panchratnam phase, the guy who first measured it. So it will turn, and that turn is the angle it subtends is related to how you bend it. Obviously, if you don't bend it at all, that alpha is 0. And the way to look at it is this k, which is the electron, saying the photon, the Poynting vector. You can think of it as it lies on a sphere, and hopefully we start making some connection to all this Berry phase and all that now. Okay? So I have a sphere with x, y, z coordinates and all that, and let's say when it got in here, this was pointing, something like that on the unit sphere or the k sphere in k space. Okay? I mean, if I were to accurate, I would draw it along the x-axis, but I mean, just whatever, it's going in that direction. And as you started bending it at all points, the k vector is going that way, right? It's moving. What's going on here on the k space? It's kind of doing some motion, going around in some way, right? And it comes back to where it was because we brought it back again in that direction. But in the process, what has happened is as you walked along, your electric field, the polarization was in a certain direction, right? Polarization of the electric field in a certain direction. And the magnetic field was in some other direction. And what we are saying is when you did this, what has happened is this triad, meaning the angle between E, H, and K, this is not twisted. We're not twisting it. This is what is called a parallel transport. Let me write that down. Parallel. Oh, wait, I'm already out of time today. Okay, parallel transport. Anyway, so you kind of turn that, and when you're back here, the electric field orientation is what I'm claiming is not quite the same, but it has changed by an angle. That's the claim. And interestingly, this alpha is equal to, if you take this area that you have gone over the sphere and you subtend it to the origin, you get what's called a solid angle. A solid angle. And then that alpha is related to that solid angle in a very nice way. In a very nice way. And I think it's like 2 pi times 1 minus alpha or something like that. Maybe you can figure it out, because if you go like that, you will have a solid angle of 0, right? So yeah, it's like 2 pi times 1 minus alpha. It's fine. I mean, so that alpha is related to whatever area or whatever solid angle this patch subtends at the origin. A nice way is you can think of a cone, right? And then the cone has a nice alpha, some angle here, and then you can relate it to what will be that alpha when it comes back. Another way, I mean, sometimes parallel transport can be confusing. So one way to look at it is if you actually, instead of a sphere like that, if you actually are going around a cone is really, if you kind of cut it and flatten it out, it's a sector like that of a circle, right? And you're doing parallel transport. What does that mean? It means, let's say let's say my vector was pointing in that direction when I started, okay? And I go around, and it's always perpendicular to that, So it's always, normal to the tangent. So when I come back here, you see there's a difference, and that's your angle. That's called parallel transport. It's always kind of perpendicular to the surface or something like that. Right? You don't twist it with respect to, say, this angle. You don't twist it. So another example is, for example, that bear, if it was carrying an arrow and it always is pointing in the direction it's moving in, all right, then you'll see it will end up in a different, the arrow, when it comes back, it's pointing in a different direction. Anyway, so that's, so that really, the quantum version of this is the Berry phase. This is the classical Berry phase. And the quantum version of it is the, Berry phase. And let me maybe outline the quantitatively what method is used. We have only 5 minutes, but I think what we can do is write that down, at least quantitatively, and the next class would be a nice time to relate it to all this, quantum Hall effect and other experimental data and transport. So Anyway, so this is the idea of parallel transport. And it's a completely geometrical sort of effect. And I think you can realize that if you are on a non-curved surface, there's no curvature, and you will not get these phases and stuff like that. Okay? So Berry phase is now related. We're going to relate it to quantum mechanics, and and to transport of electrons. And to do that, what we'll do is make a connection between. We'll start with. Let me just draw this picture now. Classical mechanics, EMAG, and quantum mechanics. Okay, so we know that we have all these three, and Berry phase appears in all of these actually. Classical mechanics. What is classical mechanics? Well, you have Newton's laws. d2x dt squared, and force is also minus gradient of a potential, right? Force is a gradient of a potential. But I think you have always felt somewhat weird, or maybe maybe you haven't, that you can always add something which is a constant to the potential, right? And if it's a constant, it goes away. Right? It doesn't. I mean, the reference frame. You're free to choose any reference you want. That's the idea. Similarly, I think you realize in electromagnetic theory, we have electric field is minus, gradient of potential. Again, here you can get V plus some constant. In fact, you can take it to be a divergence of a vector. I don't want to get into all that stuff. I just qualitatively at least. So electric field is like that. Magnetic field is curl of some vector potential, right? Vector potential, and you can actually add to that a scalar field. Okay, and the curl of a gradient is actually identically 0. So this goes away too. Right? So these are very actually, let's write it also as lambda for argument's sake for now. So these are interesting. I mean, these are called gauges. I mean, at least the name used in physics is gauge. And the idea in physics generally is that physical laws are gauge invariant. They don't depend on what gauge you choose. That's the understanding. I mean, you can choose anything that helps you in the mathematics. And then when you're done, it shouldn't depend on lambda at all. That's what's called gauge invariance. And that's a very important property. What does it mean? It means that if we are representing something physically observable, the variable we use must be, or rather, the physical observable must be gauge invariant. That's the underlying idea of many branches of physics, EMAG and all that stuff. Right? Is that clear? I mean, I think you have seen this in many times. There's no need to kind of belabor that point. I think there's a famous statement from Sidney Coleman that kind of highlights this in a nice cheeky way. He says that when I read an experimental paper, they don't say that this experiment was done in the Coulomb gauge. So that's the physical meaning of it. Meaning, if you have a physical observable, you don't care what gauge it is. So it's only the theorists that have to deal with it, right? So, okay. And similarly, okay. So the question that and in quantum mechanics now. What are the basics of quantum mechanics? Well, let's just revert back to the standard quantum mech. We have we have time-dependent Schrodinger equation is equal to h psi. I'm not doing the Dirac form, but that's fine. Again, the question that was kind of asked by Berry in late 80s, early 80s, 1984, was yes, I agree that a physical observable will requires that I have variables that are gauge invariant. What about the reverse process? What about the reverse process? Meaning, I am going to mathematically introduce something and show that it leads to something that's gauge invariant. Then, can it represent a physical observable? So that's the question that Berry asks, and the Berry phase is exactly that. It's a gauge invariant phase that came out of nowhere. You just mathematically introduced it, but then you find it's gauge invariant. And then it shows that actually it has a physical content. What is the physical content? It's like that angle that it subtends there. And that was completely missed in half a century of quantum mechanics before that. This is kind of the weird part of it. So, okay. So what we'll do now is kind of go back, and the reason it appears in such a kind of a very interesting way in quantum mechanics is because unlike classical mechanics or EMAG theory, where you depend on fields, electric field, magnetic field, forces, in quantum mechanics they have no place. There's no place for forces. There's only place for potentials, right? Right. So you, if you look at what enters the Schrodinger equation for if you write the Schrodinger equation p squared by 2m with an electric field, you must write basically the potential. Magnetic field, you must write it in terms of A dot p. So over m, A is a vector potential. There is no magnetic field that at least explicitly appears. When I write sigma dot b, in the end actually you'll see what you'll need is the vector potential always. That's what enters the Schrodinger equation. And that is kind of a very interesting difference between the classical laws and the quantum. Again, and that is the reason why what he found was this very phase related to the potential, not to the field but to the potential. So anyway, I'm just kind of qualitatively mentioning it. And I think we're kind of out of time. So let me just write down the final result here, and then next class we're going to apply it and basically do a lot of maybe hopefully interesting things with it. So what he says is, I think you realize that if I write any wave function, I can write it at time t is equal to 0. This is the nth eigenvalue of some state times e to the power minus I En over h bar, and I'm going to write it in this way. Okay, so integral from 0 to t. If you remember, we have thought of this when we were deriving Fermi's golden rule and all that. N0 is a state vector in quantum mechanics representing one of the eigenvalues, okay, pointing in something, and that thing is kind of rotating at a certain frequency corresponding to its eigenvalue. Okay. So this phase here is called a dynamical phase, and this clearly can be gauged out. I mean, you can remove it, and we did it, right? We went to this interaction representation, and this thing was gone, right? We went to another representation, it was gone. Right? Now, what Berry asks is, I'm going to actually introduce another phase, I gamma, n corresponding to the nth state as a function of t, and I'm going to actually move this vector in a certain path in time and in some space. I mean, so that's what we're going to look at in the next class. We're going to move it in some path in space. And what you'll find is gamma for a closed path, if you start at some point in, and then this is at this point, it may be somewhat hazy. If I start at some point and end at some other point, if the tip of this thing is rotating and it goes somewhere else, then you can always go back and remove this gauge. But if you close it, if you close the path, it turns out that you have a measurable non-zero phase left. And that's what he finds. And then that phase, I'll just write it down now, is basically a path-dependent phase, and it looks like this. So, closed path. So, what is this R? It could be the surface of a sphere. You're going around in a closed path on the surface of a sphere. Typically, it will be a surface of a sphere. And what we'll see is this will become the curvature later. What we have is this state, the eigenstate, and you have a derivative with respect to the path, what path you're moving in. So this is a path is here is dr. You're moving along the path. It's a dot product. It's a line integral. Of what? Of the eigenstate derivative times the eigenstate, inner product of it. And that's the very case. And we'll see, sorry, there's an I. I'll write this down more carefully tomorrow, but, on Friday. But you'll get this in, basically you start here, run through 2 or 3 steps, you'll get that. And what we'll try to make is very clear what is the physical meaning of this. And there's a question of adiabatic, meaning you have to move slowly and things like that. We're going to discuss that in the next class. But what he finds is this, and this very phase in the end is what ends up, manifesting itself as, conductance steps, and as the electric polarization in crystals, as magnetization, as anomalous Hall effect, all these other things. So this is what ends up contributing to those many things. Okay, so let's stop here, and in the next class on Friday, we will basically take it from there. And then basically you can derive an expression for any system, and you can plug it in. We'll do it for graphene maybe, and things like that. Graphene is very easy to do. So the wave functions are simple. And so we'll see for graphene that phase is pi. We'll get a pi Berry phase. And for most semiconductors, it will be 0, which is not interesting. But if you apply a large magnetic field, not 0. You get these improvements. Okay. So yeah, let's do that on Friday then.